Welcome to Worldwood Day 2021, Fire in the West. My name is Steve Ambrose, and I'm a retired Forest Service employee who now volunteers for the International Wood Culture Society, the sponsor of Worldwood Day 2021. In the last few decades, wildfire in the West has become an increasing problem for the United States and in the United States as a whole. It has caused destruction of not only our forests and our resources, but property and lives as well. Although the number of fires has actually decreased, the severity and the acreage has increased. Since 2020, about 71,000 fires per year has burned a total of about 7 million acres per year, which is double the average annual acreage in the 1990s. In cooperation with the Rocky Mountain Research Station of the Forest Service, the International Wood Culture Society is developing a series of videos to help explain what is happening in the West. And today we're going to be talking about bark beetles in relation to wildfires. Now let me introduce our participants. Jessica Brewen is a Science and Delivery Public Affairs Specialist for the Rocky Mountain Research Station. Momo Shaw is the Video Editor and Program Coordinator for the International Wood Culture Society. And today, Dr. Sharon Hood will be discussing bark beetles and wildfire. Sharon is a research ecologist for the U.S. Forest Service, Rocky Mountain Research Station, and she is stationed in Missoula, Montana. The primary focus of her research is how fire affects trees and ultimately forest dynamics. One of the specific categories Sharon is doing research on is what are the effects of fire on host tree susceptibility to bark beetle attack. Thank you for joining us, Sharon. The floor is yours.
All right. Thank you for having me. So today I'm going to discuss the effects of compound disturbances in Ponderosa Pine forest. So depending on where you live, you can probably think of how a disturbance may impact your area, from flooding to heavy grazing, hurricanes, and tornadoes. All these events shape our plant and animal species that live in a given area. While we typically think of disturbances as these one-time events, it's better to think of them as a series of events. And the pattern of these individual events, how frequent they are, how intense they are, actually is a good predictor of what species we'll find in a given area. So today I'm going to be focusing on two events, wildfire and bark beetles, both of which are very common in the Western United States. So this map shows the impact of bark beetles and wildland fire in the 2000s in the Western US. On the left is bark beetle caused tree mortality from native bark beetle species in our Western forest. And then the right shows the area where it's burned by wildland fire. So you can see that both of these disturbances are widespread in our forest, and they often can overlap and impact the same area of land. So this leads me to a lot of my research, thinking about how changes in fire regime, again, there's changes in patterns about how fires burn over time, affect bark beetles. So a lot of research exists on both of these topics because we know that fire and bark beetles directly impact our forest. What species are living in our forest, how many trees there are, and what size of trees exist, all that is heavily influenced by both of these disturbances. Less studied are the indirect effects. So we know that bark beetles can cause a lot of tree mortality, and that can in turn change the way fires burn through a forest. What I'm going to talk about today is the opposite. When fires occur, how that might change the forest ability to resist bark beetle outbreaks. So a little background on fire regimes in the Western US. This is a map showing fire regimes that have been grouped into 5 groups based on their historical or pre-European fire frequency and fire severity. The talk today is going to focus on fire regime group 1, which are low severity fires. These are fires where when a fire burns through a forest, most of those overstory trees survive the fire, and of very low frequency. So the fires would have occurred through these forests at least every 35 years. And so that's the area in light green in this map. And then I'm going to be focusing up here on the Northern Rockies. So historically, prior to European settlement in low elevation forest in the Northern Rockies, we had many forests dominated by Ponderosa pine. Ponderosa pine is a shade intolerant species, so it needs a lot of light for those seedlings to establish and grow. And these forests, again, had frequent low severity fire where the majority of those larger trees would survive. And that covered about 20 to 40% of low elevation forest in the Northern Rockies. That frequent fire created open, low density forest conditions. And that, again, in turn fostered these low intensity fires where very few trees died. It's also worth noting that Ponderosa pine forest, these are where most of the communities in the West in the Northern Rockies are either in or adjacent to. So these types of forests are also where people are living and recreating in the US. With European settlement, we've seen quite a bit of altered forest fire regimes in the US. This has resulted in reduced fire frequency from a variety of reasons, largely from organized fire suppression, where we are very successful in the US of putting out the majority of fires that occur. Also, with introduced grazing of domesticated animals, that reduced a lot of the fuel in our grasses that carry fire, so that fires just wouldn't spread as much on the landscape as they historically did. And the removing of Native Americans from their ancestral lands has also reduced fire frequency, because we know that Native Americans actively use fire for a variety of purposes. Coupled with reduced frequency, we're seeing a changing climate that is impacting our fire regimes through increased fire season length. So the fuels in a forest are just able to burn more days of the year now. And when those fires do occur, we're seeing an increase in severity. So more trees are dying than we think would have occurred in the past. And that leads to conditions like this, again, in our low elevation conifer forest, where you have these larger trees that were established prior to European settlement. And now you get this infilling of more shade tolerant species that can thrive under lower light conditions. That creates a dense forest of different species composition, and it can really change how fires burn through that forest. And what we're seeing now over large extents in the Western United States is when fires do occur in these areas where fires have not been allowed to burn as frequently, is we see these vast swaths of tree mortality after fire, where all the trees have been killed and they're much higher severity than historically would have occurred. So a little bit about bark beetle disturbances. Again, these are native insects to North America. This map is showing 3 common bark beetles and the extent that they have caused mortality in the 2000s. This picture on the right shows the sea of red trees of just how extensive the mortality can be. So I study post-fire tree mortality, and I was seeing a similar pattern to what I'm showing here, of where I was tracking trees that died. I was tracking trees after a fire to see which ones died. And then here I'm showing that there was a wildfire in 2003, and it's showing the proportion of bark beetle attacks after the fire. So we were tracking which trees were dying and which year, and also if those trees were attacked by bark beetles. And what you can see is that the vast majority of the trees were attacked in the first year after the fire. There were a few attacks in the second and third year, but it was very minor. And this wasn't due to a lack of host trees. There were still plenty of living Ponderosa pine trees in the burned area. And it also wasn't due to a lack of bark beetle pressure. So at the time of this fire, there was a large regional outbreak of mountain pine beetle in Western Montana. So there were a lot of beetles out there on the landscape actively killing trees, but we weren't seeing that mortality occurring in this burn area. Research at the same time was showing that resin flow, which I'll talk about in a minute, increases after fire. So this led me to wonder a little more about what was going on and what might be causing that decline in bark beetle attacks after the first year of fire. And so that led me to again ask, how did these changes in a fire regime affect bark beetles? And specifically, how does fire affect tree defenses, and how then does the individual tree defenses scale up to affect forest resistance to mountain pine beetle? So a little background on bark beetles and tree defenses. What you're seeing here is a mountain pine beetle that is boring in through the bark of a tree, and the tree is actively trying to resist that attack by oozing out resin. And this resin acts as a physical deterrent to the bark beetles to try to keep the bark beetle from entering the tree. And it also acts as a chemical. There's toxins in the resin that kill the beetles. So if the tree can produce enough resin to overcome the bark beetles that are attacking the tree, then the tree will survive. If the bark beetles overwhelm those tree defenses, then the beetles can reproduce in the tree and the tree dies. Here's a few more pictures about mountain pine beetle. They're small beetles about the size of a grain of rice, and they bore into the tree's bark and they excavate these linear patterns of, here on the left, you see they're called galleries, where they lay eggs and the larvae overwinter and mature into adults. It takes about a year. And then those beetles emerge from the tree to go attack living trees. This is the life cycle of the mountain pine beetle. The big takeaway from this here is that one mountain pine beetle can't kill a tree. Mountain pine beetles work through coordinated effort to mass attack trees. So they work in concert to overwhelm those tree defenses, and they can't start to successfully reproduce in the tree until those defenses are overwhelmed. So once these defenses are overwhelmed, that's when the beetles start to mate and reproduce. And at that time, it's a kind of point of no return for the tree. The tree will die. So here's some information about defenses in Pinus species. On the left is showing a wedge of wood, and these horizontal canals are resin ducts, and they're also vertically in the tree. So this horizontal and vertical network of resin ducts creates a storage system for resin. So on the upper right is a picture of a tree core, and each light and dark band together represents 1 year's worth of tree growth. And what's really nice about wood is it allows us to go back in time to retrospectively look at the growing conditions for a tree. And because resin ducts are embedded in the tree's wood, this also allows us to go back in time and see how defenses have changed with the tree. So these black outlines are showing some of the resin ducts in the tree. This is just a pencil mark, so you can ignore that. But again, this offers a way to see how resin duct defenses are changing over time. And this bottom right picture is just showing a close-up of vertical resin duct. Here is the large one, and then the horizontal resin duct in blue. So that again, when a beetle is boring into the bark, that severs one of these resin ducts, and the resin can be delivered via the resin duct to the wounding site. So resin ducts are important because they act as sites of resin synthesis and storage, and also delivery. And we know that more resin ducts equal more resin flow. So the resin is the actual defense against beetles, but anything that increases resin ducts should also increase resin flow. So that resin ducts are a much more consistent measure to obtain than resin flow, which is highly variable and just offers a snapshot in time. So this picture is just showing that the more resin duct area a tree has, the higher the resin flow. and therefore the more resistance a tree should have to bark beetle attacks. This slide is also showing that resin ducts are a good surrogate for resin flow as a measure of a tree's defense. So this is showing trees that resisted bark beetles and survived versus those that are susceptible. So they were attacked and ended up dying from bark beetles, and against duct size. So these resistant trees had larger ducts, and they also had more of their wood or tree ring in duct area. So again, showing that trees with larger resin ducts and more area in ducts are more resistant to mountain pine beetle attack. So how does fire enter this picture? I wanted to look at how low severity fire affected resin ducts. So we cored trees of inside and outside of burned areas. Again, these were trees that survived the fire so they could continue to grow and produce wood, so we could see how the fire impacted the tree growth and resin. And we also cored trees outside of the burned area to act as a control or baseline for what resin ducts may be doing regardless of fire. So here I'm showing two sites, one in Montana and one in Utah, and it's showing before the fire and after the fire. And these are our control trees. So even though it's before and after the fire, these are trees that are outside of the burned area. So they're unburned trees, again, acting as our control or check, because we know climate and several other things influence resin ducts. So there's a little change, but nothing statistically significant in these unburned trees in the years before and after the fire. But if we looked at the burned trees, you see an increase in duct area after the fire, showing that resin ducts are increasing after a fire in the trees that survive. So this led me to ask, does duct production decline after fire exclusion? Because remember that in the United States, we've seen large alterations in historical fire regimes. And so I wanted to know if by excluding fire from areas that historically burned very frequently, if we might be causing a decline in trees' defenses and making forests more susceptible to mountain pine beetle outbreak. So I was lucky to be able to use cores that had been collected from 3 prior studies of fire history. And these were sites where the research had shown that they had burned very frequently, about every 3 to 20 years prior to European settlement. And the last fire had been at least 80 years before. So we had the exact year of when fires ceased due to organized fire suppression and other reasons. But we also had one site that had no fire exclusion. It was deep in a wilderness area, and fires had been allowed to occur throughout the 1900s. And so what I'm showing here is before and after that fire cessation period based on the fire history studies. So this is looking at about 75 years before 1925 and after 1925 to see what the changes in resin ducts have been. This site is showing where fires have continued. So this site acts as our check. So because fires actually were allowed to continue throughout the 1900s, I didn't expect to see a decline in resin duct area. And that's what we found. The 75 years before and after European settlement in this area did not change resin duct area. But on the site where fires had stopped after 1925, we see this decline in resin duct area, suggesting that these trees are less resistant to mountain pine beetle now because fires have ceased. That same pattern was found at the site in Oregon, where there was a decline after the fire cessation period that here happened in 1870. This is suggesting that by removing that frequent low severity fire from these Ponderosa pine systems, we are directly changing the tree's physiology and defense system and how the tree may be able to withstand a mountain pine beetle attack. So lastly, I wanted to ask how management actions may impact forest susceptibility to mountain pine beetle. I used a site from the National Fire and Fire Surrogate Study that's located in Western Montana. This study included 4 treatments. We had a control where nothing had happened. There hadn't been a fire in any of these areas in about 100 years. Again, they're all dominated by Ponderosa Pine forest, but there had been a lot of encroachment and establishment of Douglas fir, which is another common species in the Northern Rockies. The second treatment was a prescribed burn only, where we conducted a low intensity fire designed to also be low severity. So again, to not kill many of the overstory pine trees. Then there was a thinning only, where that thinning was designed to remove a lot of the Douglas fir trees and open up that forest to make it more resistant to a wildfire and make it more to where if a wildfire did occur, fewer trees would die. And lastly, there was a thin and burn, where these areas received the same thinning prescription and then followed by a prescribed burn. So this study was originally installed to look at the effects of these fuel treatments on changes in fire behavior and many other ecosystem responses. What we couldn't predict at the time of the study's establishment was that a few years after the treatments were implemented, there was a mountain pine beetle outbreak that started to heavily impact the area where the study is located in about 2005. So this allowed us a pretty rare opportunity to look at a study that is set up with an experiment that's set up with statistical replication and to study the effects of a naturally occurring mountain pine beetle outbreak. It's one of the few times these types of conditions have aligned. This slide just shows a little more context about where we are in Montana and the Northern Rockies, and the study is here in Western Montana. The red here are forests that were impacted by the mountain pine beetle outbreak. The inset shows the 12 treatment units. And what I want to show here is just that these units are all surrounded by red. So these units were challenged by the mountain pine beetle outbreak. There were beetles in the area. There was mortality going on throughout the experimental forest. And so again, allowing us to directly test the impacts of these treatments on resistance to mountain pine beetle. Here's a few photos of the treatments in 2005, just again, a few years after the treatments were implemented, but before the mountain pine beetle outbreak began. So what you can see here, the control there, it's very dense. There's Ponderosa pine and Douglas fir trees. The burn only killed some of the smaller trees, but not a whole lot. Again, it's hard to implement a prescribed burn successfully with only one burn. That usually it takes repeated burns to achieve open conditions. Just to call your attention to some of the differences between the thin only and thin and burn, the overstory conditions are very similar in the thin only and thin and burn. But you can see that that prescribed burn killed a lot of the smaller trees and really opened up the understory compared to the thin only. So what did these treatments do to tree growth and bark beetle, or resistance to bark beetles? Here I'm showing on the x-axis time, and the arrows show the year of treatment implementation. On the left, I'm showing basal area increment, which is a measure of how fast a tree is growing. So these trees were all growing about the same rate prior to the thin and burn. And this is no surprise that study after study has shown that when you open up a forest through thinning, those residual trees have more resources so they can grow faster. And that's exactly what we saw. And the green lines and pink lines show the thin only and thin and burn. Right after those treatments, those trees start growing faster relative to the control and burn only. And we see the same pattern when we plot total duct area, as where with the increase in tree growth, there is also an increase in the amount of wood that has resin ducts. So faster growing trees also lead to more resin ducts. We saw a little bump in resin ducts in the thin and burn treatment relative to the thin only, but it wasn't nearly the response that we saw from the previous studies I showed you that were all from wildfires. So the main results of the study showed that these fuel treatments that were designed to reduce the intensity of a future wildfire were also extremely successful at reducing the intensity of a mountain pine beetle outbreak. I'm showing the percent of Ponderosa pine that were killed during the outbreak that lasted between 2005 and 12 by order of treatment intensity. So these light gray boxes are showing the variation within all the plots that were within the treatment units. So you can see there's big differences from plot to plot that are shown because of this large spread. But if I call your attention to these dark black bars, those are the medians. So that's the most common value that occurred in each of the plots. What you can see is that the control where we did no action, about 50% of the Ponderosa pine were killed. And the burn only, it was about 20%. And then the thin and burn median values were 0. So very, very few trees were killed in the thin and burn during the mountain pine beetle outbreak relative to the control and burn only. And what this means for the long-term outcome of the forest is it really changed how these forests are going to develop over time. Here I'm showing the same order of treatments, but now I'm plotting the ratio of Ponderosa pine to Douglas fir. So again, Douglas fir is a shade-tolerant species that will out-compete Ponderosa pine in the Northern Rockies. And without disturbance, we see a forest of increasing dominance by Douglas fir and eventually Ponderosa pine dropping out of the forest. So positive, anything above 1 is there's more Ponderosa pine trees than Douglas fir trees. And the light gray bars are showing before the outbreak, all treatments had some level of dominance of Ponderosa pine. But because of the thinning, the thin only and thin and burn treatments were the most dominated by Ponderosa pine, which again is what we would think reflected historical conditions. So after the outbreak is shown by the dark gray bars, and that shows now that in the control, there's actually more Douglas fir trees than Ponderosa. The burn only, it's about equal, but the thin only and thin and burn are still heavily dominated by Ponderosa pine, showing that these forests are more resistant to the mountain pine beetle outbreak, and therefore they are also more resilient. They should be able to continue to persist as Ponderosa pine forests for much longer compared to the control and burn only units. These are the same pictures in 2005 that I showed before, and then 10 years later in 2015, that reflects about 15 years post fuel treatment and 5 years after the mountain pine beetle outbreak. In the control, you can see that a lot of those trees that were killed by the beetles have now fallen, and they've increased a lot of the fuels on the forest floor. Not a whole lot of changes in the burn only. The thin only, you can really see the impacts of these small trees now growing up to create a lot more ladder fuels that could potentially change fire behavior in the future. And the thin and burn is where we see the longest lasting effects of their still open forest dominated by Ponderosa pine. So the thin and burn is effective for much longer at reducing potential fire behavior as well. And so kind of the big take home messages here that our dry pine forests that were historically maintained by frequent low severity fire and or now have fuel treatments or restoration treatments that use thinning and fire, we can increase our resistance not only to wildfire, but also bark beetles. And with that, thank you for listening, and I'll take any questions you have.
All right, Sharon, thank you very much for that presentation. Anyone have any questions?
I feel like you have found the perfect solution for this problem. I don't know. So do you guys know what caused the outbreak of the bark beetles?
Yeah, so generally mountain pine beetles outbreaks begin by these are native beetles, so they're always out there on our landscape. You might see them killing 1 or 2 trees per hectare every year, but you don't really notice them that much unless you are keyed into what you're looking for. But every now and then climatic conditions align, mostly through very dry conditions, so droughts and high temperatures. that can cause tree defenses to that resin I talked about. It's harder for the tree to make that resin. So it's easier for those beetles to overcome the defenses. Also, with warming conditions, more of the beetles overwinter successfully, so the populations can sustain themselves from year to year. So it kind of sets up this suite of conditions that where the beetle populations can start to gradually attack larger and larger trees, and it's kind of like more room at the end, like a big hotel versus a tiny little bed and breakfast. If there's enough beetles to overwhelm a big tree's defenses, then it can produce many more beetles. The reproduction rate is higher, and then the following year, all those maturing new beetles emerge from those larger trees, and then there's even more beetles, and they can attack more trees. So it starts to grow exponentially from year to year until finally either through predation or a change in the drought conditions allows the populations to crash and go back down to those really low levels again.
I feel like they almost live in the tree, almost like a parasite. But I saw that parasite usually don't kill their host.
Exactly.
But instead, they're not that smart. They just I want to eat all of you.
Yeah, it is very different than most parasites or other insect herbivores, where there might be causing some stress to the plant, but not outright killing the plant. So, but there are numerous bark beetle species around the world that do this.
Sharon, I have a question about climate. It seems like when the tree produces resin, that's pretty dependent on moisture. If there's no moisture, the resin production for the tree would be down. Any idea about what effect the moisture or lack thereof might have on the resistance to the bark beetle by the trees?
Yeah, we definitely see a reduction in resin flow when there's extreme drought. So that was one of the reasons that around 2010 to 2015, there was an extreme drought in Southern California, and that we saw a huge outbreak of bark beetles in that area during the drought. And it's because defenses were so compromised in the tree. And it's also the tree's not able to grow hardly at all and produce wood. So then resin ducts are also not being produced.
I have a question for you, Sharon. I know you talked about how resin ducts, the amount of them can kind of fluctuate through time, based on if there's fire, sometimes they increase. Is it the younger trees or the older trees that are more adaptable as far as producing more resin ducts?
Yeah, that's a good question. I don't think that's been directly tested. The results that I showed you came from a variety of tree ages. So maybe really, really old trees, it might start declining because growth could be declining, but I don't think we know that answer yet.
In your presentation, you mentioned that the resin duct, they would increase or grow because with the thinning, also the burning treatment. And with the thinning, I kind of understand because after the thinning, the trees can grow faster and better. But why does the burning has anything to affect how tree would decide to grow their resin duct?
That's a great question, and we don't really know yet. Resin ducts it's a general wound response. So we also know that producing a lot of resin can help seal off wounds. So, and you might have seen fire scars on trees, or like where porcupines feed on tree stems. And pines, because they produce so much resin, it allows it to seal off that wound and prevent any pathogens from entering the tree and decay from starting. So, it could be associated with a tree that can actively seal over its wounds. Also, it might be kind of a residual effect of that response that is also happening after fire, but we really don't exactly know the mechanism yet by which fire causes an increase in resin ducts.
Probably it's kind of like another self-defense system for them to protect themselves.
Absolutely. Yeah. Because other tree species that don't produce as much resin, if a fire happens and it kills part of the tree stem, we see a lot of decay happening quickly, and then the tree will eventually die. But pines, because they can produce so much resin, they can withstand those little injuries or wounds that occur during a fire.
Sharon, you showed one of your slides a pitch pocket where the tree had actually pitched out the bark beetle. And you said that there was a chemical in the pitch that actually could kill the beetle. Is that pretty effective for the tree, or how effective is that for the tree to pitch that out? How effective does it kill the beetle because of the poison?
I think it's highly effective. So that resin, it's a really complex mixture of a whole bunch of compounds. And there's been a lot of studies trying to isolate individual compounds, which we've done, and see what their effect is on the beetles. But it turns out there's not really one silver bullet. It seems to be that cocktail of compounds that kind of are toxic to the beetles. It actually gets a lot more complicated by the beetles. Sometimes it can affect the ways the beetles communicate with each other by allowing it's all through pheromone communication.
Right.
So it's initially that resin and the pitch that I showed acts as a physical barrier, but what happens as the beetles, they're in the tree, the toxins also work with associated fungi that are come in with the beetles. The chemical toxicity part is a huge part of the tree's defense. It's not just the physical part.
I feel like we can change the theme to look how smart trees are.
Yeah, I was trying to. Yeah, it is. When I started down this path with tree defenses, we think of trees just kind of landing wherever the seed landed and growing and putting up with whatever comes at them over the centuries. But they're very much living in their environment and responding to their environment, much more than we give them credit for.
When the forest fire happens, how come they don't kill the beetles? Do they fly?
Oh, yeah. So they certainly can kill the beetles. They do fly, but they spend the majority of their life under the bark. Yeah, inside. And so kind of right at that interface between where the bark and the wood is where they live. And so bark is a really good insulator from heat, and Ponderosa pine especially has thick bark. So those beetles probably don't even see or feel the heat at all. There are pine species with thin bark, and if the fire is intense enough, that could cause beetle mortality as well. And if the fire kills the trees outright, it also dries up the phloem where the beetles are living and their food source. So then the beetles die as well. So the beetles need living trees to be able to survive and reproduce. So they don't attack dead trees.
So I have another question for you, Sharon. I know that you mostly talk about Ponderosa pines, but is there, as far as progression goes and mountain pine beetles, the epidemic kind of starting and increasing and coming back down, is there certain species that it starts off with and then moves to other species, or is it or certain elevations that it starts at and then they move, or is it just shotgun wherever they go, they go?
This may be better answered by an entomologist, but I can or generalize it some. So mountain pine beetle is one of the most generalist aggressive bark beetles out there. So mountain pine beetle attacks most pine species. We'll see it. Lodgepole pine is probably a better host to mountain pine beetles. So we see attacks often starting in lodgepole pine forest, but that's not always the case in places like the Black Hills, where there's very few lodgepole pine. We see plenty of attacks occurring and starting in Ponderosa pine forest. So this beetle species is highly adaptable to many pine forests. As far as elevation, it's really kind of dictated by where these drought conditions are starting to occur. So oftentimes it is the lower elevation forest, and then beetles moving up into the higher elevations during the progression of the outbreak.
So it's more about conditions, and they're not very picky.
Yeah, they want to attack the largest, healthiest trees, but again, they usually can't because there's not enough beetles on the landscape to coordinate a successful attack. And so it's only during those outbreak conditions where we start to see those larger trees being attacked and killed.
It looks like with your research, we kind of can recognize that with thinning and burning, controlled burning, it's a really useful way to help the forest to resist a bark beetle attacking. Have you guys been practicing it in, most of the forest, or like what kind of difficulties would you encounter when you try to enhance these kind of actions?
Yeah. So thinning and prescribed burning are both commonly used throughout the United States for a variety of purposes, but it is like for our fuel treatments where we're trying to change the way a fire may burn through a forest, that thinning is very common, and prescribed burning is common in some regions of the US and becoming more widespread across the US. But the challenges are, well, with thinning, there's different social acceptance sometimes with thinning, and also it's definitely more accepted are being used in our areas that we call the wildland urban interface, where you have our communities and people living adjacent to forest. But thinning can also be more expensive, but it's also more reliable. You can do it under a variety of conditions. But some areas are too remote to do any thinning, or maybe the lands are steep, or some of our wilderness areas where management actions aren't allowed, we can't do thinning. Prescribed burnings, I think it's maybe more socially acceptable, except with the large caveat of people don't like to breathe smoke. So we're really limited on good burning days of when smoke disperses easily through the atmosphere. So the challenge is to be able to have plans in place to where we can really take advantage of those good burning days and be able to conduct prescribed fires over more area.
So Sharon, I know you study a lot of the Ponderosa in the West, but is there a progression from kind of the southern part of the western half of the United States, and are you seeing a progression kind of going north, where as far as like beetles attacking and the different stages that the forests are in, as far as like as you continue north in the United States?
It's more that there are different beetle species in the southwestern U.S. than the northern U.S. So you might see it in California, parts from the southern Sierras to the northern Sierras, sometimes progression with another beetle species, but not so much that I can really think of.
In one of your slides, it shows like how the forests are occupied by the bark beetle spiking. And I remember a really huge area is actually in Canada. I think in British Columbia area. I suppose that if the bark beetles are increasing tremendously there, it will affect a situation here in the States, or at least in the closer states, right?
Yeah, I mean, there's certainly a lot of research that goes on mountain pine beetle in Canada. There, it's mostly for lodgepole pine. There is a progression of mountain pine beetle and lodgepole pine forests from the north to the south, and actually moving into a species of jack pine that we don't historically, we didn't see beetle attacks. Again, these are native insects, and there has been a lot of effort to kind of be reactive, and a beetle outbreak is occurring. What are we going to do? And trying to implement emergency measures or herbicides and cutting attack trees. And that has proven pretty ineffective, that really the shift has become how can we be proactive about creating resilient conditions in our forests to withstand a variety of disturbances. So it's much more about promoting forest conditions that we think could easily be better positioned to withstand drought, bark beetle attacks, fire, because we know all these disturbances at some point are going to impact our forests. We just don't know exactly when or where. So it's more just trying to be proactive rather than reactive.
Well, I'd like to thank Sharon today for her very informative presentation. And I hope you've enjoyed our presentation today. And I sincerely hope that you will tune in to future videos prepared by the International Wood Culture Society on various topics concerning fire in the West. You know, the partnership that International Wood Culture Society and the Rocky Mountain Research Station have, I think, is an excellent example of how organizations can work together to inform the public on various items such as wildfire in the West. Thanks for tuning in.